Hello, my name is Zahan Bukhari, Bio 201 and 202 TA here at Tempe, and today I'd like to talk to you about respiratory physiology, specifically gas laws. Now there are 5 main gas laws that we want to discuss today, and we really want you to understand that physics governs the respiratory system at both the macroscale and microscale. So we'll start by talking about the ideal gas law, and then get into some of the more obscure ones like Henry's law, Dalton's law, Fick's law, and the law of Laplace. So first off, the ideal gas law really governs the respiratory system at the macro scale. So remember that air expands as it's warmed. For pressure, we want you to think of an empty baster or a bellows pump used to inflate the pig's lungs in class. If you squeeze an empty baster, then you'll notice that its volume decreases and air rushes out, because fluid flows from an area of high pressure to an area of low pressure. So if you've ever heard of this law before, we are looking for the one that's V equals nRT over P. But for Bio 202, all we want you to remember is that volume is directly proportional to temperature and volume is inversely proportional to pressure. So if temperature increases, volume increases. If pressure increases, volume decreases. A law that you might not have heard of before Bio 202 is Henry's law. So first, we want to discuss the more commonly known Dalton's law and partial pressures. So if we have a mixture of gas, or fluid as it were, we can decompose its pressure into a series of partial pressures. So you know how air is composed of nitrogen, oxygen, carbon dioxide, and water vapor primarily. So we can actually decompose the 760 torr that make up air pressure at sea level into a certain pressure contributed by nitrogen, a certain pressure contributed by oxygen, a certain pressure contributed by CO2, and a certain pressure contributed by water vapor. The most important thing for Bio 202 is to remember in fresh air, the partial pressure of oxygen is relatively high compared to the partial pressure of carbon dioxide, which is relatively low. If you were to look up this law on the internet, or if you were to use a physical chemistry textbook, its general form looks like this. So the pressure or partial pressure of a species A equals some constant that depends on the solvent, so blood in our case, which is very close to the constant for water, times the concentration of that compound A dissolved in the solvent. So for Bio 202, we just want you to remember that the amount of a substance A dissolved in a solvent is proportional directly to the partial pressure of that compound A at the solvent's liquid gas interface. So physically that means that having more of a certain gas by the blood will actually increase its solubility. Thus, CO2 is more soluble in the tissues that generate it, and oxygen is more soluble in the lungs where there's fresh air. So gas exchange occurs at this place, 2 places simultaneously. So it's physically easy when you have fresh air coming in, there's a lot more oxygen in fresh air. The partial pressure is higher, that makes it dissolve relatively easier. And then CO2 at the same area, partial pressure is lower, that will allow the blood to kind of kick out the CO2 into the air that you'll breathe out. And then in the tissues, this case is reversed. At the same time that you're bringing in fresh air through your lungs, you're bringing in fresh oxygen, your tissues are generating CO2. And now the partial pressure of CO2 outside those tissues is relatively high, so you can load the CO2 into the blood without any issue. However, the oxygen's partial pressure out there by the tissues is relatively low, so it will unload easier and get into the tissues, get out of the bloodstream. Okay? So, now that we've discussed those laws, let's talk about Fick's law. Now, Fick's law governs diffusion, and you don't have to memorize this monstrosity, but if you were to look it up online, this is the one that we're talking about. The flux of a compound A equals some constant times the negative gradient of that substance's concentration. And then that constant approximately equals the Boltzmann constant times temperature over 6 pi times molecule's radius times the viscosity of the substance. What we want you to know for Bio 202 is just the rate of diffusion is directly proportional to both the surface area of what it's diffusing through, the pressure gradient, and it's inversely proportional to the membrane thickness. So that means if surface area is increased, then diffusion will occur faster. If a pressure gradient is increased, then diffusion will occur faster. But if the membrane thickness is increased, then diffusion will occur slower. And I really want to emphasize surface area here. So if we have our alveoli, they look kind of like spheres. So let's take a yellow sphere and a blue sphere. A yellow sphere with radius 1 micrometer and blue sphere with radius 2 micrometers. Notice how when I double the radius, it doesn't double the surface area and it doesn't double the volume. The surface area to volume ratio actually changes. So notice how the surface area is 12 micrometers, divide that by the volume 4 micrometers, you have a 3-to-1 surface area to volume ratio with this small sphere. But when the sphere gets bigger, the surface area to volume ratio drops to 3-to-2 here. So a doubling of spherical radius causes a 4-fold increase in surface area and an 8-fold increase in volume. And for this reason, smaller spheres are better for diffusion. So smaller the alveoli in your lungs, the faster air can diffuse into and out of it. But we can't allow the optimization for surface area to go unchecked. There is another law that works kind of against Fick's law, and we call this the law of Laplace. So the general form, there's more than one law of Laplace, but if you look this one up, it's the one where you see the pressure differential, or specifically capillary pressure differential, equals negative surface tension times the divergence of a normal vector to a surface. For Bio 202, we just want you to know that capillary pressure differential is about 2 times the surface tension over the spherical radius. So smaller pockets of air, I should say smaller r, are more prone to collapse than larger ones. It's best to illustrate it with an example. If you have 2 balloons connected by a straw, notice that there's less air in the yellow balloon than in the blue balloon, and we let the edges of the balloons go and let air flow between the two, you would think that air would flow from the blue one into the yellow one and the air would sort of equilibrate. In reality, this would result in more latex being stretched if the air were to equilibrate than it would be here. So what happens when you let the balloons go? The yellow one actually collapses and it goes all flat. You can kind of visualize this by imagining yourself blowing up a balloon. If a balloon is completely flat and all deflated, it's pretty hard to blow air into it. But if it has some air in it already, it's relatively easy to inflate. So now we have a problem. Smaller alveoli or smaller spherical radii result in the balloon or the alveolus being more prone to collapse. Alveoli actually avoid collapse in healthy people by secreting what's called pulmonary surfactant. Not bile surfactant, but pulmonary surfactant. It's like a soap or a detergent that reduces the hydrogen bonding in water and allows the actual capillary pressure to go down. So that way, the spherical radius of alveoli can become nice and small and you won't have to worry about them collapsing. However, this is a very delicate balancing act, and if anything doesn't operate correctly in the respiratory system, it's physically prone to trapping air in the lungs or the alveoli collapsing or all sorts of respiratory disorders. So if the surface area of alveoli decreases, so we make them bigger and bigger, we don't have to worry about them being squished shut. We don't have to worry about them being collapsed because the pressure differential is relatively low. So here's normal alveoli, and here's larger and larger alveoli. When this happens, however, there is much less surface area for how much volume of air there is in the lungs, and you can't get as much oxygen into the bloodstream. Moreover, you actually end up trapping air in the lungs because it's difficult to squeeze air out of here. We call this emphysema, where these alveoli become confluent, and you see they have merged into much larger alveoli. You can't get air out very easily, and the lungs just keep inflating and inflating gradually until it's very difficult to inflate them and get fresh air in. And that's why we say emphysema often leads to barrel chest, because the chest expands and ends up looking kind of like a barrel. But at the same time, if we make the alveoli smaller, yes, you can get fresh air in easier and you can get diffusion to occur at a faster rate, but you are at risk of alveolar collapse. Now, of course, in a normal person, you don't have to worry because of pulmonary surfactant. But in premature births, sometimes infants don't make sufficient pulmonary surfactant, and you can imagine air rushing out of here if a balloon were to be squished flat, like these alveoli here, and you were to try and breathe in, try and inflate a balloon from a completely flat and deflated state. It's very difficult, and you can see these infants have quite a bit of difficulty breathing in just because their alveoli cannot stay open. So thankfully, in a healthy person, these systems work, or these laws work to create a nice happy medium between the two. And then if someone were to have respiratory distress syndrome, you could actually treat that by adding pulmonary surfactant to their system until they can produce their own. So for your practical, we won't have you do any sophisticated calculations with any of these gas laws, but we do want you to expect multiple choice or true false or fill in the blank questions, and to be ready for any physiological applications. Maybe I'll change the names of two gas laws and see if you can pick it out, true, false, that I switch the names. Or maybe I will use a disease example like respiratory distress syndrome and ask, what is it? Is it the capillary pressure, or is it the size of the alveolus causing conflation, and or is it the air being moistened or warmed and moistened as it's taken into the body? What causes respiratory distress syndrome? Be ready to answer these sort of physiological application questions, and don't worry too much about the math. Thank you, and I hope this made understanding respiratory physiology easier for you.